You know, there's this incredible material in our bodies that we almost never think about, but we rely on it every single day. It's our silent shock absorber, our smooth bearing surface. It even shapes our ears and our nose. Today, we're diving into cartilage, the real unsung hero of our entire skeletal system.
I mean, it's a question we all start asking at some point, right? A knee that creaks going upstairs, a hip that aches after a long walk, and you might think it's the bone. But more often than not, the real story, the real answer is in this remarkable tissue that covers it. So let's take a closer look.
To really get what's going on, we have to go microscopic. What you're looking at here is the inner world of cartilage. And you know, it might look pretty simple, but its unique structure is both its greatest strength and, as we'll see, its biggest, most tragic flaw.
So what is this stuff exactly? Well, the textbook definition is a resilient connective tissue. But what does that mean? It really boils down to two main things. You've got the cells, which are called chondrocytes. Think of them as the tiny builders. And then you have all the stuff they build around themselves, which is this complex web called the extracellular matrix.
And here's the part that is just wild. Over 95% of cartilage isn't even the living cells. It's the matrix. So while the cells are really sparse, it's this huge non-cellular structure that's doing all the heavy lifting, absorbing shock, resisting all that pressure, and giving us that incredibly smooth surface for our joints.
Okay, so let's dig into how this natural cushion actually works. Because it's not a one-size-fits-all kind of material. Our body has actually engineered different types for very, very different jobs.
In fact, we can break it all down into three main varieties. Each one has its own unique recipe, which makes it absolutely perfect for where it is and what it needs to do in the body.
First up, you've got hyaline cartilage. The word that always comes to mind for this one is glassy. It's incredibly smooth, almost frictionless, which is exactly what you want lining your joints. You'll also find it in your rib cage and your windpipe. Then there's elastic cartilage. This is basically hyaline cartilage, but with a whole bunch of elastic fibers woven in for flexibility. Perfect for, say, your external ear. And finally, there's fibrocartilage. This is the real tough guy at the group. It's packed with dense collagen, making it the ultimate shock absorber for places that take a beating, like your knee menisci and the discs between your vertebrae.
And you can really see the difference here, can't you? On the left, look at that smooth, uniform matrix of the hyaline cartilage. The little cells just look like they're floating in this glassy sea. But now look at the fibrocartilage on the right. Whoa! You can clearly see all those thick, wavy bundles of collagen. It's a perfect example of how structure completely defines function.
All right, now let's go even deeper. Let's get right inside that matrix itself. We're zooming way in, down to the molecular level, to see what this amazing material is actually made of. This is where the real magic is.
The recipe for cartilage is, well, it's pretty surprising. Look at this. The single biggest ingredient by a long shot is just water. 60 to 80% of it is water. The rest is basically a scaffold of proteins. You've got about 15% collagen, which gives it strength, and 9% of these special molecules called proteoglycans, which it turns out are the key to holding on to all that water. And the cells themselves, barely 5% of the whole thing. Okay, this is my favorite analogy for how it all works. Think of those proteoglycans as a kind of molecular super sponge. They have a negative charge, so they pull in and hold on to huge amounts of water. And that's what makes the cartilage so plump and resilient. But a sponge by itself is pretty weak, right? That's where the collagen comes in. The collagen fibers act like rebar in concrete, creating this strong, tension-resisting framework that holds the whole sponge together. It is an absolutely incredible piece of biological engineering. So who builds all of this? Who's the mastermind? That job falls to this one cell, the chondrocyte. I love this description of it as the lonely architect, because each one is responsible for creating and maintaining this enormous, complex matrix all around itself. And here you can see them just kind of hanging out in their little homes. Each chondrocyte lives by itself inside this little space called a lacuna. As they work, they basically wall themselves in with the very stuff they're creating. Sometimes, though, you see them in these small clusters, which are called isogenous groups. And that's a little clue that tells us the cells have divided pretty recently. Okay, so we know what it's made of, but how does this tissue actually grow and expand? Well, it turns out it has two different tricks up its sleeve, and they're most active when we're young and growing.
The first method is called appositional growth. The easiest way to think about this is like adding new layers of paint to a wall. It just builds up on the outside surface. The second method is interstitial growth, and this one happens from the inside.
This is where those existing chondrocytes divide and start making new matrix, expanding the whole thing from within, kind of like a loaf of bread rising.
But here's the twist in the story. For all of its incredible strength, for all of its brilliant design, cartilage has a secret weakness. And honestly, it's a really big one. So here's the bottom line. Despite being under constant stress, day in and day out, cartilage is absolutely terrible at repairing itself.
And there are 3 really big reasons why. First, and this is the most important one, it's avascular. It has no blood vessels. Nutrients have to slowly diffuse through that dense matrix to get to the cells. It's like a neighborhood with no roads. Getting supplies in and taking the trash out is just incredibly slow and inefficient. Second, the cells are trapped. Remember those lonely architects? They can't pack up and move to a construction site if there's an injury. And third, in adults, those chondrocytes almost never divide. So basically, the construction crew is tiny, they're isolated, and they never hire any new workers.
And look, this isn't a small problem. As this quote from a major histology textbook puts it, cartilage shows a striking inability to heal. That means even a tiny minor injury is often a permanent one.
So this one biological fact, this inability to heal, has huge consequences for our health, especially as we get older. It basically sets us up for a lifelong challenge with our joints.
Because it can't heal, all that normal wear and tear just adds up over a lifetime. This gradual loss of the cartilage cushion is what we call osteoarthritis. It's where that smooth surface wears away, and eventually you can end up with painful bone-on-bone contact. So what does that breakdown actually look like inside the tissue? Well, on the left, you've got healthy cartilage. It's plump, it's full of water thanks to those proteoglycans, and it's got a smooth, resilient surface. But on the right, in osteoarthritis, those crucial proteoglycans are lost. The cartilage literally dehydrates. It becomes brittle, the surface starts to crack and fray, and that damage just keeps going until it reaches the bone underneath. And that really leaves us with the ultimate question, doesn't it? Cartilage is an absolute engineering marvel. It's a living cushion designed for a lifetime of work, but it's a cushion that can't be restuffed. And that raises the critical challenge for all of us. If this amazing tissue can't heal itself, what new strategies will we need to protect our joints so we can maintain our mobility for a full, active life?